So far we've seen two different kinds of quantum states, pure states and mixed states. And we've been thinking of mixed states as probability distributions. A mixed state is simply a mixture over pure states. And so a natural question is, what does this mixture represent? So we say that a mixed state is in state psi with probability p. Where does that probability come from? Where does this uncertainty arise from? And so what we're going to see in this lecture is that in fact every mixed state arises as the reduced density matrix of a pure state on a larger system. So the fact that we are in a mixed state, a state that is not pure, so a mixed state that has rank larger than 1, reflects the fact that this mixed state must be part of a larger system. That larger system is in a pure state, but we don't have access to the whole system. And this is why we end up with a density matrix that has rank larger than 1, so a mixed state that is not pure. So let's see how these purifications work. So we've already seen before that density matrices can arise by taking the reduced density. And the sort of prototypical example is if you start with an entangled state like this psi here, which is initialized in an EPR pair. So let's quickly compute the reduced density on A. We know how to do that. We have to choose a basis B for the B system. Here it's appropriate to choose the standard basis for B. So let's choose this. To this basis, we can associate POVM elements that represent a partial measurement of the B system in the basis B. So this would be M0, which is the identity on A, tensored rank 1 projection on 0 for B, and M1, which is the identity on A, tensored the rank 1 projection on 1 for B. We can choose as cross operators the same as the M's because they're projectors. This lets us compute the reduced densities. If you do the computation, you'll see that you'll get the outcome 0 with probability half, and in which case you get the state Ho0 on A and B, which is simply 0, 0. Or you could get a 1 with probability half, the state will be Ho1. And so this tells us that the reduced density on A is the totally mixed state. Half of the identity matrix, half of the projection on 0 plus the projection on 1. So here we have a pure state, a global state, it's entangled. I take the reduced density on system A and I obtain a mixed state. And the question is whether this process is reversible, or more generally, if whether given a density matrix, we can always write it as the reduced density on the system of a pure state of a larger system. And the answer is yes, and let's see how that works. So let's take an arbitrary density matrix Ho-A. We know that we can write it as a mixture with here some coefficients pi that are non-negative and sum to 1. These are the eigenvalues of the reduced density matrix, and the psi I, which are the eigenvectors. So you can always compute this decomposition using the singular value decomposition. So the way we interpreted this is by saying that, all right, this is a mixture, and what it means is that with probability pi, the state on A is in the pure state psi I. So where does this probability arise from? Who gets to decide what state we're actually on? And so now what I claim is that I can introduce a new state on A and a new system B, where B is going to be the system that controls which I we get. So it's natural to introduce this state, psi AB, which is going to be the sum over all I. And let me put root pi, psi I on A, tensored I on B. Where B is a new system, let's have this index AI range up to the dimension of the system B. So B, this is a new system. It has the same dimension as the A system, and it has a basis that I called I. So this is certainly a pure state. It's a valid state. It's normalized because the norm of psi will be the sum of the pi's, which is 1, because Ho-A was a normalized density matrix. And now let's check that it achieves what I claim it does. So we have to compute the reduced density of psi AB on A. How do we do that? We choose a basis for the B system, we measure, we see what happens. So of course, what basis are we going to choose? The one we just introduced. So let's use that basis for B. Then if we compute the probability that we get a certain outcome I, we're getting used to this now, is just going to be the squared norm of this vector square root pi psi I, which is pi. And the corresponding projected state ρi will be psi I on the A system tensored I on the B system. And so this tells us that the overall reduced density ρa on the A system, obtained by taking the partial trace operation, will be the sum over I of the probability that we get I, this is pi, tensored with the reduced density on A that's associated with ρi. So that's just the rank 1 projection on psi I. And you can verify that, as claimed, the result that I obtain here is exactly the state that I started from. And I didn't make any assumption about that state. This was just an arbitrary density matrix on A. So any such state that can be obtained the way that I've obtained it, or in any way that is such that it's reduced density on the system A, this is called a purification of the reduced density.